Good morning. Welcome to Krishna's classroom. We continue our exploration of the consequences of the Heisenberg theorem. And we shall just recall the statement of the theorem. So we have proved, stated and proved stated and proved the Heisenberg theorem in the context of R. Every closed and bounded yeah. Any compact any compact sorry, making okay, let me in the whatever we have proved so far, what we have proved is that let J be a closed bounded interval of R, then A J is compact. This automatically calls for, we have proved this itself. This automatically calls for exploring the converse, that is every interval compact, or does it mean that an interval in R is compact if and only if it is closed and bounded? Okay, let us explore this problem. Now, look at the following. See, let us look at the various intervals of R. What are the intervals of R? See that we have unbounded intervals, classified as minus infinity to A, minus infinity to A, where A is included. Then you have A to infinity. A is a generic number. A infinity. And of course, you have minus infinity to C. These are the unbounded intervals. Where A is a generic number, that means for any A, for every A belonging to. Don't think that you should have the same A here. They could be different. So these are all intervals. Now these are all unbounded intervals. And you can, for each one of them, you can create a open cover which has no subcover. Can show or exhibit an open cover with no finite subcover. Is not compact. So these unbounded intervals are obviously not compact, because see, we are exploring the converse of this result. Okay? And a typical, for instance, and from this you can improvise. See, you can show that minus n to n with no finite subcover. Similar statements you can make for each one of this. Okay, and also you see that you can devise an open cover even for this, okay, or for this, right? So they are not compact subsets of. So these are unbounded. Now we go to the bounded. See, we have AB, and A These are the typical. So for minus infinity, less than a, less than b, or less than or equal to b, less than. So these are bounded intervals. But they are not closed. And one can prove that device a open cover for each of them having no finite subcover. For instance, you can see this that for AB can be written as P and R and this has no finite this cover. No finite subcover, finite subcollection, which provides cover. Therefore, this is not compact. Similarly, one can prove that these two are also, though bounded, not compact. So all of them are bounded. Sorry, all of them are bounded intervals, and they are not compact. So that leaves out only this. So remark. It proves that an interval is compact of if and only if is bounded and closed. See that none of them is closed. Okay. That is this of the form A. So what we proved in the Hein-Borel theorem is that every closed bounded interval AB is compact, and we prove that if it is not of this form, then it is not going to be compact. I mean, that's what we have investigated. Okay. Therefore, together we obtain that an interval, a subinterval of R is compact if and only if it is of the form a closed bounded interval, if it's both closed and. So, closed and boundedness characterizes the compactness of intervals. Okay. So, that is the moral of the story. See, look at the way in which we have proved it. We have shown that a closed and bounded interval is compact. And then we looked at all kinds of intervals of R, and we proved that each one of the intervals which is either not bounded or it is not closed or both can be provided with an open cover, which has no finite subcover, therefore that is not compact. So together these two facts put together would give you that an interval of R is compact if and only if it is closed and bounded. So that's the moral of this. Now we go further from that. Now we look at some more examples of this kind, namely example. This we have explored in detail. Consider this, that is a S the sequence 1 by n. Now we have already seen that not compact. It's quite easy to show that this is not compact because all that you need is to produce a open cover which has no finite subcover. So you can see that S is contained in the, we are talking in the context of R, it's contained in minus delta n. Where delta n is a positive number 1 by so if you take this kind of open sets, then you can pack 1 by n into that, and clearly this each one of these open sets will contain only one of these elements, Therefore, there exists no finite subcollection of see, this is what is happening. 1 by n, 1 by n plus 1. This is 1 by n minus 1. So, you are taking a collection. So, you see that you are taking delta n that lies between these two. So, this is 1 by n or 1 by n plus 1. So, this is this point, this is this point. So, this is the delta n that you are talking. Okay. So, you can always do this, right? You can always do this, and you see that it contains only 1 by n. Similarly, you can take an open cover for which contains only 1 by n plus 1, etc. This collection is an infinite collection, and open sets which provides a cover for this S, but it has no finite subcover. So, this is not compact. On the other hand, suppose you take S bar you are joined to this number 0 also, point 0 also. Then S bar is the reason is to take care of 0, you will have to put a open set. This is 0 minus epsilon to plus epsilon positive. Okay. So, you can, and because this is a neighborhood of 0 and 0 is in this collection, this is the a open set of this kind is absolutely essential to take care of 0. Then you see that for epsilon positive, there exists an n such that for all n greater than capital N, collection 1 by n belongs to this interval. Converges to 0. This implies given epsilon positive, there exists a n epsilon such that for every n greater than n epsilon, we have So this is satisfied, and therefore what you have is this collection delta n epsilon subcover, because all that you need is take n greater than or equal to less than or equal to n. Sorry. So you have a finite number of sets of this kind plus one more to it. So there is a finite subcover which gives a covering for S union shear. And you see that each one of them except the last one contains only one element. Because what happens is when you take this minus epsilon to epsilon, it absorbs the tail of the sequence 1 by n. Okay? And therefore, only finitely many of them are left out. And you will have to only take care of those finitely many. Okay, so this we have analyzed in detail. Therefore, this is compact. Now, more generally, if X is a metric space, and Xn is a sequence of points in such that then the cos some epsilon compact, but it's just repeating the arguments that we have. Now we want to explore the problem which subsets of R are compact. Okay. So our main concern is now, or we expand so far we had been talking about intervals. Okay. So the question that we take up at this stage is this is one question. Is it possible to characterize? Is it to characterize? Characterize compact so we'll continue to work in R and see whether you can characterize compact subsets. Okay. So in this direction, we prove the following theorem. Let us start explorations of this. So we have the following. What is that we would expect from our experience of working on intervals of R? We would possibly like to explore whether closed and bounded subsets of R are compact and vice versa. Okay, that's our objective. Okay, so we would like to characterize these sets. Say that something like a subset K of R is compact if and only if it is closed and bounded. So that these two properties together would characterize compactness. Okay, so we'll make our explorations in this direction. So our expectation is this. Let me also put it down here. So we expect to show that K contained in R is compact if and if K is with an additional condition. We have already proved it. What is the additional condition? That K is an interval. Okay. Now we want to drop that condition if possible. Okay. So is it possible to show that K is compact if and only K is closed and bounded? Okay. Right. So in this direction, we'll prove some results. Let X, this is a very general result, be a metric space. Then we prove that K is compact implies K is closed and bounded. That means in one direction we put this here. Okay. K is compact implies K is closed and bounded. That means we are verifying that all compact subsets have are bounded and closed, and in the negative direction we can use it. If one of these properties fail to hold, then that set cannot be compact. So okay, I'll make a remark about it towards the end. So let us prove this. We first prove that K is bounded. So we have assumed. So we assume K is compact. That means every open cover has a finite subcover. Now the first thing that we verify is first claim. K is bounded. So let us see how we use compactness to prove this. So the situation is this. You have got R. This is a sort of Venn diagram type thing. Or we are doing in a metric space, therefore we are this be X. So more general. Now K is a subset of. Now we want to show that, or we assume K is compact, and we want to show that K is bounded. That's what we want to do. So K compact. Okay, consider let X belong to X not belong to. Consider the open collection of R positive. That means all balls of radius R with center at X naught. So see, X naught may be inside K or outside K, it doesn't matter. So let me take X naught inside K and draw the picture. So what I am having is, I have balls like this. So what I have is balls of this kind. This is for some R1, this is for some R2, this is for some R3. So this is B X naught R. Now clearly, so this is a it's an uncountable collection that we have devised here, which forms a count. Now, what we have is that since K is closed, K is compact, this cover as a finite. That means if you want to say that there is some R1, R2, etc., Rk such that this is, but it's redundant because you see that suppose R1 is less than R2, then E x naught R2 covers that part. Okay, so you see that it is a finite subcover, which implies there exists an R positive such that K. That is, this becomes a cover for K, and that implies K is, that is precisely what you mean by K is bound. So that completes the proof of that part. Okay. So there is some R, like say this is one. The radius is which encloses the given K. This is the K. The K is completely enclosed in that ball. Now we want to show that it is closed. Now the next claim is K is closed. Yeah. So this is what you have. X, and this is your K. And to show that K is closed, it is enough to prove that, it is sufficient to prove that K complement open. So that's our strategy. So we are going to prove that K complement. Now this is K complement. Now, how do we show that a set is open? To show that, you take an arbitrary point of that set and show that it has a neighborhood which lies entirely in that set. Okay. So we choose an arbitrary point x belonging to K complement. Now choose an arbitrary point y belonging to. So let x be K complex. So let X be an arbitrary chosen point in K complex. We choose a Y which is an arbitrary, which is a any point in let now you see that dxy is greater than z. So what we do? So let dxy, which is positive, let ry now b y ry intersection b x ry is empty. Clear? Okay, this is empty. Further, the collection b y ry provides K with an open curve. Since K is compact, there exists y1, yk, or you can use 1n, such that the collection b yi r yi subcurve. Here is where we have used the compactness. Okay. So what one does is choose minimum of they are all positive numbers, therefore there is a minimum which is certainly positive. Minimum exists because it's just finite number of positive numbers, therefore now what we are going to claim is the following. Now we claim that, so this is the scenario that you have. This is your x, this is your a, this is your x, this is y. So you have y1, y2, etc. yk. So you have got r1, etc. Such points. So each one you have y1, y2, etc. Correspondingly, you have got 10 orders. Okay. So this is actually Ex. So what we are going to prove is the following. What we are going to prove is the following. See, we have P yi r yi intersection B x r yi is empty for I equal to 1. This is the same thing. Okay. Then what we have is P x r is empty for I equal to but you know every element of x belongs to one of these collections. Okay, since RYI okay, every element of every y is in every y belonging to K belongs to one or more of okay. So what does it mean? Empty, which implies K intersection which implies K compact, and since X is arbitrarily chosen, it follows that K complement. That is if and only K is hence we have completed. So that completes the proof of. So every compact set in a metric space is closed and bounded. Now some remarks. The question that we wanted to ask was this: does closed boundedness characterize what are called compact sets in space? Now, one can just make a remark, the first remark, the same result holds good partially in all Hausdorff spaces. That is a compact of a Hausdorff space is the compact subset of a Hausdorff space is closed. Now we can prove the following, that is, now we prove that, but is the converse true that we have to explore? Sorry, is the other part true? Is it also a compact subset of a Hausdorff space is bounded? We'll ask this question. Now we prove that. So the next question is every post a compact set? Oh, this is the next question that we use. So we will prove this statement. Okay. Assume. In fact, the answer seems to be yes. Okay. This is a very useful tool doing compactness. Let K be a subset of the metric space straight away take the metric space to be compact. Closed subset of the compact metric space Now what we claim is K is compact. Now we see that since X is compact, every open cover now let U alpha an open cover alpha belonging to some index. Open cover for K. Now K complement A being closed, K complement is an open, so hence U alpha union K complement is an open cover X. Since X is compact, there exists a finite subcover for this open cover. That is, there exists U alpha 1 comma U alpha 2 comma U alpha K union and K complement as a cover for which implies the collection U alpha equal to alpha I equal to 1 to K is an open cover for thus we have shown that for every arbitrarily chosen open cover for K, it has a finite subcover. And hence K is compact. So all closed subsets of compact sets are compact. So that is this proves that all closed compact now we will explore some problems, general problems. Some examples. Oh, these are exercises rather. A, comma B, compact implies compact. It's quite simple. Every open cover for A has a finite subcover. They are all in the context of some matrix spaces. B also for any open cover has a finite subcover. So you take any open cover for A union B. Okay, just certainly a finite subcover, right? Similarly for A intersection. The second problem. Let zero be the metric therefore you should use a matrix space. Now G is also a group with respect to multiplication. With 1 as the identity. Given A and B positive numbers, their product is again a positive number. And then of course 1 is the identity element. You can prove that for every A positive, 1 by A is positive and A into 1 by A equal to 1, and of course associative, commutativity, all those things. That's a commutative. So you have essentially two structures here. On G, we have a topological structure induced by the crucial metric. And the group structure, that is algebraic structure, induced by usual multiplication. This is the group structure. Now the question that you ask is the following. Which subgroups are common? Which subgroups of G? First of all, we observe that singleton 1 is a compact sub. Consisting of only one finite number of, okay, right? That's obvious. It's a finite sub. Now you take any x then you see that x to the power n but is it this is not compact because one can so of course x to the power 0 is taken as 1. Okay, I mean it's exactly as we worked out an open cover sense. This is possible. Okay, these are all going to be spaced. You can find out open set or choose an open cover. Each of which contains only one element to the power n from then it cannot have a finite subcover. That's a trick. Now a third example, you take C star. C star is So 0. Again, this is a group. Now one can show exactly you prove that one is the uh, only compact subgroup. So one can show that. The set of all Z belonging to C. That is the unit circle. Is the only compact subgroup of now we prove this statement that any closed bounded subset of R is compact. This is what we know. So let K then K is bounded nice. K is contained in infinity. For some. Now you see that minus M is compact. So you know something about the intervals. Since K is closed, of R it follows that compact. Therefore, what we have proved is that every closed bounded subset of R is compact. And if you take a compact subset, then it is closed and bounded. So we have proved the following. K is K compact implies it. K closed and bounded in R implies K is compact. Putting together, we have a subset of is compact if and only if K is closed and bounded. So that's what we were trying to. I want to make a remark that this result is not necessarily true in all metric spaces. Necessarily true. There are some weird metric spaces where things go wrong. Okay. So example, let X be an infinite set with discretely. That is, the discrete metric is that dxy equal to 0. Okay. This is the discrete. Now you see that x is closed. It's clear. Because any metric space is closed. Okay. And x is bounded. This is because dxy equal to 1 so 1 gives a bound for it. Okay. But x is an infinite set. You can construct a open cover. So what are the compact sets in this space? In this space the compact sets are in this space the compact sets are only the okay. I will explore some more problems in our next lecture. So, thank you very much. Most probably I will be coming back today afternoon again. Okay. Thank you very much.